Going to talk about applied soil chemistry. I know that just strikes joy and excitement and enthusiasm for most of you. I actually like it, and I think it's important. So hopefully you'll be able to endure this brutally long lecture. I might recommend just kind of cutting this up into pieces and working on your unit quiz alongside of it, so it's not quite so long. I normally give this lecture over several classes, so it's a little bit lengthy. I think it's important to learn how to separate ourselves from the rest of the pack. It's important to have excellence in what we do. And I believe that what I'm getting ready to teach are some things that will help us do that. For example, if you look here in the bottom right, we're told all the time that sports turf that's mowed short can't grow more than 2, 3, 4 inches, and yet there we go. That's Lavelle Edwards Stadium, and it's got roots that are about 8, 9 inches deep. This picture in the background on the left is from my front lawn, and you can see from the time of the year, it's really not during the growing season, and yet my grass is really green. Now, how do we do that? I think that's what we're looking for is excellence. And some of what I'm getting ready to talk about is helpful in those areas. I think it's really important to not only just admire the beauty of plants above ground, but it's important to realize that below ground part of the plant is really important. It's critical to understand soils. And so I think it's important to stick our head down there and figure out what's going on. So that's what we're going to do today. It's important to realize that soils are not all the same. Now, sometimes we can see some of that, and sometimes we can't. Sometimes we can dig down and actually see some physical differences like are here. But a lot of what I'm going to talk about today are differences that are not always immediately obvious, the chemistry stuff. We generally try to fix problems with more water and maybe more nitrogen. That's pretty common, and yet sometimes we're just compounding our problems when we're putting on more water, more nitrogen. So we need to actually determine what is wrong. I like to say that we need to learn lessons from our farmer friends, most of whom have learned how to depend on soil and tissue analysis in order to do what they do. And for some reason in the green industry, we just haven't seemed to caught on like they have. And so I would point you to their success. I like to say, don't guess, soil test. That's a good mantra. Starts with a good sample. I'm not going to really talk about how to do soil sampling. Lots of sites. Here's a couple you could go to in terms of how to take a good sample. If we don't take a good sample, it's garbage in, garbage out. If you have a bad sample, no amount of good soil testing is going to solve your problems. So important to do that step. There's lots of instructions, some written by me, such as this or others. Well, let's talk about soil pH first. It has a lot to do with the chemistry of the soil, and so we need to understand soil pH. pH is defined as the negative logarithm of the hydrogen ion activity. The hydrogen is the protons. This acids are really important. It can impact the solubility of a wide variety of elements. Some of those are nutrients. Some of them are not, like aluminum's not a nutrient, but there's a lot of it in soil. And if it becomes too acidic, that aluminum will start to solubilize and it will harm plant roots. Manganese is another one that can become toxic. Now, manganese is a nutrient. And so at high pHs, for example, we may not have enough manganese because the pH actually inhibits its solubility, and plants need to kind of drink their nutrients. The nutrients need to be in the soil solution in order for the plants to get to it. And so at a high pH, there may not be enough. As the pH is lower, more and more of that manganese becomes soluble to the point where it could actually cross over from being adequate to toxic. So those are important concepts, is the pH will affect the solubility. Typically, as we become more acidic, that acid sort of dissolves things in the soil. Optimum pH is neutral. We hear that, and that's mostly true. Neutral is 7. Below that is acidic, and above it is alkaline or basic. We have 4 different soils here, kind of some case study. We've got an acid soil with a pH of 4.5, buffer pH of 6.5. I'll explain what that buffer pH is in a minute. A neutral soil with a pH of 6.8. Now, it's not exactly right on 7, but it's close enough. I mean, we would call that neutral. An alkaline, non-calcareous soil that has a pH of 8.2 with 0.1% lime. An alkaline calcareous soil with the same pH, but this time it's got 12% lime in it. Now, limestone is commonly found in these alkaline soils. And that's what determines whether a soil is calcareous or not. Most alkaline soils are calcareous. These soils tend to be in arid and semi-arid regions like Utah and basically the Western United States, most of it, where we don't get much rainfall. We tend to develop alkaline soils, and that limestone tends to accumulate in those soils. As we get into high rainfall areas, that stuff kind of dissolves and sort of washes away, and we are depositing hydrogen from the water, and it makes the soils more acidic. So high rainfall areas tend to be acidic, low rainfall areas tend to be alkaline and also calcareous. So how do we manage these? If we kind of just look at these different things, we can see the terminology there: acid, neutral, alkaline, calcareous. We got different pHs. We have different levels of limestone in those soils. Now the acid and neutral soils tend to, don't have that limestone in them. Limestone will dissolve in an acid soil, and it can actually be used to raise the pH. That's what we use it for. But it exists naturally, and it really oftentimes at unhealthy levels. Having limestone in the soil isn't necessarily a good thing. Now, we can kind of manage around it. It's not the end of the world to have a calcareous soil. We have lots of beautiful landscapes in these calcareous soils, but that's kind of how it works. It's very dominant in the chemistry. Now, the buffer pH thing is really important. We only do that on soils where we feel like we potentially need to raise the pH on these acid soils. And so we'll do another test that will determine how much limestone we might need to raise that pH. Essentially, the buffer pH test, it sort of simulates the limestone. So if we add some limestone to a soil, how much is the pH going to come up? Now, and this is really important because in a soil that is not very buffered against change, such as a sandy, low organic matter soil, it doesn't take much limestone. And so that buffer pH is going to go up high. So the higher the buffer pH, basically the less limestone I would need, because it's telling us that that soil is not buffered against change. It's easy to change, in other words. Soils that have more clay and or organic matter in them are going to be more buffered against change. Those colloids are the clay and the organic matter. Those are the colloidal materials. They have lots of surface area in them, and they tend to buffer a soil against change. So if I've got a lot of clay and or organic matter, that soil is buffered. So it's going to take more limestone to raise the pH. And that buffer pH test will kind of tell us that. It'll give us an approximation of where we need to be. Now, if I look at that 1800, a lot of times soil test labs are going to report that value that you need in terms of limestone in pounds per acre. In the urban landscape, we usually are not talking about acres. We're usually talking about per 1,000 square feet. Those tend to be our recommendations for fertilizer and limestone. So in order to convert that, there's 43,560 square feet in an acre. So that just means that in order to convert to pounds per 1,000 square feet, I just divide by 43.56 in order to convert that. So if I wanted to do that, it would be dividing 1,800 by that number. Now, if I want to raise acid soil pH, first of all, I need to determine if it's even necessary. Now, the lower it is, the more likely I am to need to do that. But also, there's another factor in there. Sometimes we see low pHs and we got really healthy plants. And sometimes I'm asked, well, why? Why are my plants healthy? sometimes it's just the chemistry. I don't have those toxicities. And so it's not just a pH thing. It's also, the pH is sort of enabling the toxicities, so to speak. And so it's possible to not have that. I'll refer you to this ABC document in terms of the values of those toxins, aluminum and manganese in particular, and in terms of deciding whether we want to apply limestone to an acid soil or not. Now, once I decide if I want to apply the limestone, the amount is once again, that is given to us in terms of that buffer pH test. Now, the value we got here on this lime requirement, that's assuming that it's pure calcium carbonate, which is limestone, that's really finely ground or finely divided material, which means it's extremely reactive. If the limestone's not pure, and most of the time it's not, and or it comes in large particle sizes, it's not as effective. It doesn't work as well. And so we might have to do this adjustment. And what we do is the limestone has what we call a calcium carbonate equivalent test, or CCE. We run that test on the limestone. And then let's say it comes back with a 50% number. Well, that means it's going to take twice as much to do the job as, highly effective 100% material. So we just simply divide that number. So if I had a 50% CCE on this sample, instead of 1,800 pounds per acre, it would be 3,600 pounds per acre. I would just take 1,800, divide it by 50%, and that would tell me how much material I would need to apply based on its effectiveness. Okay. I'm not sure if you heard that or not, but my house alarm went off, so I had to pause. Getting back to soil pH. Again, ideal is kind of that neutral area. Below 6.5 technically is kind of where we start seeing trouble. It's really below 5.5 where we really start seeing some major trouble. Usually I'm pretty okay if I'm at pH of 6. One thing you got to realize though is you might get some variability across the landscape. So if your pH comes back 5.8, right at those spots where it's 5.8, you probably don't have any trouble, but you might have some spots there that are below that because it's not perfectly uniform. So that's important to realize. Now, above 7.3, these alkaline pHs, we tend to say you kind of live with it. We're not going to recommend lowering the pH in most cases. There's two reasons for that. Number one, we can really just manage it with nutrition. It needs a little more of certain nutrients. And also, it's just not practical to lower the pH. There tends to be so much limestone in our soil and water that it's buffered in the alkaline range. And so we're going to go broke if you try to lower that pH. Now, getting back to the acid soils, here's a photo I borrowed from a good friend of mine, Dr. Gertal from Auburn University, showing some negative effects. Here's some centipede grass, and it actually looks, pretty good, even though the pH of 6 is acidic. It looks pretty healthy, and even at 5, it looks pretty healthy. But over here, down here at pH 4, we're really starting to see some negative effects of that low pH. So that's also some kind of reality check to know that it doesn't always just happen right at when it turns acidic. It can be a gradual effect. Also, as I said previously, this pH thing can affect nutrition. This graph is everywhere, and I kind of hate it because it's got some incorrect things that it just sort of implies some things that are not true. When Dr. Truog put this thing together back in the 1940s, he didn't really intend it to be misused, but yet it's been widely misused. If you Google nutrient, pH, soil stuff, this is what comes up. But it really sort of, again, implies some things that aren't true. So I've kind of created this one that I think is better because it shows us There is an interaction, but it also says why there's an interaction. So in the acid soil area, we get less nitrogen and sulfur, molybdenum, because of microbial things. Microbes are like plants; they kind of have that optimum pH range, and if the pH is bad for them, they're going to kind of lose their activity, and so we might get less nitrogen being mineralized. Now, this is really important, though. The phosphorus solubility, that can be really negatively impacted by pH. Now, what happens there, I'll explain in just a minute. But it's, the more acidic, the less soluble that phosphorus is, to a point. Another thing that can happen, and it's not quite as important, but we do get hydrogen competition, leaching kind of things that are going on. So this would be more relevant, especially in sandy soils that get a lot of rainfall and we're not really irrigating. We can kind of push some of these cations through the soil, like the calcium and magnesium, that normally wouldn't be deficient in most soils. But in those particular soils, we can see that. And we tend to see that more in the acid soils that have been acidified and water's kind of pushed through them. And it's not that the calcium and the magnesium nutrients are really, their solubility isn't really affected, but it's just, there's just less total of them there. So that's kind of more of the reality. On the alkaline side, we also get less nitrogen, but it's not because of the microbial thing as much as it is volatilization. We can lose nitrogen when the pH is too high, nitrogen fertilizer. But we also get the poor solubility thing. And notice that phosphorus is here. So it's a problem both at acid and alkaline pH. I'll show you that in just a second, as well as some of the other, some of the micronutrients, zinc, iron, manganese, copper, boron, can also be affected in terms of their solubility. So we're more likely to see those. We deal with them by making sure that we do soil testing and we add them when they're needed. Okay, so here's the phosphorus one. Again, what we're looking at here is on the y-axis. This is the extent of retention. In other words, the higher we are up on that, the less phosphorus is going to be available for plants because the soil's hanging on to it. You'll notice there at about 6.5, that's the optimum pH for phosphorus availability. Above that, we start getting these calcium phosphates, also magnesium as well, but they start forming these precipitates. And it's solid form. And again, plants kind of need to drink their nutrients. The phosphorus needs to be in the soil solution. And when they're in solid form and calcium phosphates, the plants can't get to them as easy. And on the other side, in the acid soils, we get these iron and aluminum phosphates that form. So that's what happens pH chemistry wise. Now, just an aside here. Realize that most irrigation waters are hard water, which means they contain calcium and magnesium carbonates. Now that carbonate is really the kind of the key to the chemistry, and we start developing these. And most of the time when I'm irrigating in these regions, and that's, again, these are arid, semi-arid places. And so I'm typically irrigating and I'm applying water that's usually hard water, and I can be applying upwards of 500 pounds of limestone per year through the irrigation water, which again kind of tends to buffer that up high, and that is really critical. Now once again, this carbonate, it's not the calcium and the magnesium that is really the important thing here. It's the carbonate that kind of causes the problems. Calcium, magnesium, they're really not the issue. And that's also true with the acid soils as well. I failed to mention that, but it's when we apply limestone to these acid soils, it's not the calcium and the magnesium that's raising the pH. It's the carbonate. It's the anion side of that that's doing the job. So it's, here it's that CO3. So again, calcium carbonate, the CO3, the carbonate, is what's the kind of the active chemistry thing that's going on. All right, so let's kind of talk more about this nutrition side of things. We've got essential and beneficial elements that are needed by higher plants. For example, here's a phosphorus. This is St. Augustine grass that's phosphorus deficient, and so we're interested in that. In terms of some of the things that can happen nutritionally, we're also interested and not overdoing nutrients in terms of getting pollution in the air or in the water. Those are reasons why we want to manage nutrition. And so we want to do things right in terms of soil testing in order to avoid both deficiency and pollution. So we get these essential elements. This is a little dated. We'd probably add cobalt and nickel to this slide as they're also essential micronutrients for most plants. But these are the guys we need, and they're kind of divided out into groups here. When we do soil testing for these, and some of these, we don't do all of them. Some of them we're not interested in testing for, but we kind of get two different types. And this is going to get a little complicated, but I'm going to try to help you understand what you need to know. And I'm going to dive in just a little deeper than what you need to know, just to kind of give you the background information here. But we sort of have two types of nutrition tests. We have what we call a total quantity, as well as an availability index test. So the total would be situations where we're extracting the entire amount of an analyte, such as nitrate. I want to extract all of the nitrate from the soil. I'm not extracting all of the nitrogen because there are other forms of nitrogen, such as nitrogen that's bound up in organic matter. I'm not extracting that per se. Now, same thing with sulfur. I'm interested in extracting sulfur, but there's other sulfur in the organic matter. But when I'm doing my test, I'm interested in extracting all of both of those as well as chloride. So those are a little different than what we would call the availability index tests, which is the rest of them, phosphorus and potassium notably, as well as some of the micronutrients and the secondary nutrients. So these are availability index, which means we're trying to simulate a relative amount that's available to plants. That gets a little complicated. So, why don't we just analyze the total phosphorus? The reason is because when we do, there's no correlation with that number and plant fertilizer response. So it doesn't do us any good to report those. We can do that. We can do total phosphorus tests, but no correlation. So it's not a good test. What we want to do is extract and measure the amount of available nutrients while excluding the non-available forms, so in the case of phosphorus, like we might have rock phosphate, that plants just aren't going to see that. It's there in the soil, but it's in a solid form that plants can't get to. So when I'm doing my soil test, I don't want to include rock phosphate. I want to include the stuff that's available. I'll show you some more of that here in just a minute. And we're trying to do, when we're doing the science on this, we're kind of trying to simulate what a plant's doing. And we don't need to worry about that for this purpose, but that's what these tests have more or less been kind of shooting for. We need to verify this. Now, this is important. We need to verify these soil tests with nutrient uptake and yield studies to see, is there a correlation? I'll show you that in a minute. Kind of just sort of looking at the phosphorus thing here just a little more in depth. So this is kind of representing the soil. This area up here is the soil solution. Here's a phosphate molecule that's soluble, floating around in soil solution. Now, if a plant gets that, it can take that phosphate in and utilize it. But the other fate that can happen to that phosphate molecule is that it can hit a surface, such as in this case, an iron oxide surface, and we get a ligand exchange reaction that happens that essentially binds the phosphorus down here to that surface. And once that happens, it's not very plant available. That could come off later. I mean, that's a possibility. It could be released back into the soil solution, but for the time being, it's not plant available. Here's kind of a picture of what this looks like. This is a great little experiment where some calcite was, and this is a laboratory test, but calcite was put into a test tube, and this here on the left is 0 phosphorus, and the one on the right's got 50 parts per million, and you can see actually the phosphorus that is being precipitated on the surface of this calcite, similar to the previous one where we showed it with iron oxide. The calcite can also be a surface that the phosphorus can be precipitated on. And once again, it's not very plant available phosphorus unless it redissolves into the soil solution. So here's kind of another diagram of this. We get what we call non-labile phosphorus that's sort of locked up inside the minerals or even the organic matter of the soil. And that's not very plant available at all. We also get some adsorbed phosphorus that's right on the surface. That's a little more available. It's more likely that that's going to get released to the plants. We call that labile P. So we get adsorbed P and precipitated P that are on those surfaces. And then we have phosphorus that's actually in solution. And now that's what the plant's going to take up, and it's got to be like that. So what'll happen is plants take that out of solution, we get some equilibrium chemistry. It's complicated, but the bottom line is that it sort of forces some of this other phosphorus back into solution. And so we get this kind of back and forth thing going on. If I put on a bunch of fertilizer, it actually kind of goes to the left and deposits. And as plants take phosphorus out, we get some phosphorus being released. And so it's a really kind of a complex system and I'm trying to represent this in a soil test. And, it's a little bit of a stretch, but that's what's going on, whether we like it or not. And so we're trying to represent that in the soil test. So sort of bottom line here is and again, continuing on with the phosphorus thing is I want to extract what's currently soluble. So any phosphorus that's floating around in the soil solution, I want to get that. But I also want to get these slowly soluble forms of phosphorus that might become available through the course of the season. And then I want to exclude the insoluble stuff. Now, we don't have anything that does that precisely. We have some chemical extractants that approximate it. And that's what we do with soil testing with these index values for phosphorus, potassium, and some of these others. So here's kind of the bottom line. Again, I kind of dipped deeper than maybe what you need to know, but what is good to realize is that when I'm doing soil testing is what does it mean? If I do a soil test, do I get any kind of a correlation to anything that's meaningful? So if I'm looking at this data, I'm saying, you know what, that's meaningful. That's a tool I can use to help manage phosphorus. And so what I'm looking at is I'm looking at yield response over here on the y-axis, and I got soil test phosphorus levels on the x-axis, and then each one of these dots is a data point. That's a field study that we've done where we've gone out and measured fertilizer response. Now, if the unfertilized check plots give me the same plant growth as the fertilized ones, that means I didn't get any fertilizer response. And I would divide those numbers and I would come up with 100%. In other words, the check plot yielded 100% of what the fertilized plot did. So for example, if you look at this value right there, that's, it's sitting at about 22 parts per million soil test phosphorus, that was basically no response. Now, in contrast, let's say I get a value down here like this one that's sitting down at about 7 parts per million soil test phosphorus. It was a 50% number, which means that my control plots grew about 50% of what my fertilized plots did. So by putting fertilizer on, I got a huge response. So what this is telling me is that the low soil test phosphorus values on average gave me a nice response when I fertilized them. And up here, when the soil test was high, I didn't get a response. So that's good information. Is it perfect? No. You'll notice some outliers here where we didn't really get, or where we didn't get a response, even though the soil test was low. And then on the other hand, we get, up here, we get some where we got a response, even though the soil test was high. So it's not a perfect system, but pretty dang good. I'm pretty pleased with those kind of numbers. I feel like I can use those numbers and feel good about it. That's kind of reality. You'll notice that basically somewhere above about 25 parts per million, I'm sort of done with getting a response. Now, some people would look at that and say, well, wait a minute, I still got some responses even up to almost 40 parts per million. So, okay, if somebody wants to argue with me, and I might say, hey, well, we're above 25, let's stop putting on phosphorus. And if somebody's a little uncomfortable with that, honestly, it's really not going to hurt me. It's not going to really hurt the plant to put on some phosphorus if my soil test is 35 parts per million. It's not really going to hurt the environment. Now, if I keep going though, if I keep going up too high, you'll notice that's starting to curve back downwards. And we actually have data that shows that if I'm putting fertilizer on, when I get really exorbitant values, I'm not showing those here, I can actually get a negative plant response when I put on phosphorus when the soil test is super high. And I also get some negative environmental responses too. So the point is at some point you need to stop putting on the phosphorus fertilizer, okay? Now, some soil tests for certain nutrients are going to look more like this one, where we get a pretty steep drop off fairly quickly. Phosphorus isn't really like that. I'm just showing this as a contrast. Some nutrients like boron or copper, they would be more, even nitrogen would be more like this. This is actually a nitrogen graph. So the sort of the plateau of where we're optimum, I've got less flexibility there. Phosphorus, I've got a pretty wide plateau up here. I'm okay, between 25 and, on this graph, 45, 50, I'm okay. But, this graph, no, I'm not okay. I'm going to have to kind of nail that a little tighter. And so that's important to realize. Again, some are more critical to not over apply than others. Mostly it's nitrogen, copper, and boron. Most of the rest have a fairly wide plateau. So that's good to realize. Also, so this is a little bit of a, kind of a reality check. It's a little frustrating to look at this. And let me tell you what we're looking at. So this is an IPNI. IPNI was the International Plant Nutrition Institute. They no longer exist, unfortunately. But they used to do this soil test summary every year. And one of the things they did is they surveyed all the state extension agencies. And so every state has a land grant university. It's a government operation, and part of their job is to look at soil tests and provide interpretation values. And so what this is looking at is the critical Bray phosphorus. So Bray P1 is one type of a phosphorus extractant. I'll talk about that more in a minute here. But what you're seeing here is that states don't always agree. These state extension agencies don't always agree on what the critical level is, where we should stop putting on phosphorus. You'll notice we're seeing numbers as low as like 13 in California and Nevada, and as high as 100 over here in this province in Canada. Now, there's some explanation for that. And the one in Canada, it's because they're mostly growing potatoes up there, and potatoes are one kind of an anomaly, a crop. They really need a lot of phosphorus, but on average, we're somewhere between, roughly 25 and about 45. And so some people would look at that and be a little discouraged, but you know what? I'm like, whatever, it's like, as long as I'm not going too crazy high, I'm okay. Soil test is still, it's not precise maybe. And there's some reasons for some of these differences, different soils, different crops, different weather would be reasons why you would get different interpretive values. So again, some people kind of freak out about this kind of thing, but I'm not too worried about it. I think it's fine. I just, in the urban landscape, if I could get people to stop fertilizing past 50, I'd be pretty happy actually. And you'll notice hardly anybody's above 50. And so we can kind of agree, they can kind of all agree on at least that. And that to me, good enough. Potassium would be similar over here on the right. Okay, now I've mentioned these different tests. So there's various extractants have been developed over time. And that's true. I'm showing just phosphorus and potassium here. Phosphorus is kind of the biggest deal because there's some really big differences in these tests. I'm going to explain that in just a second, but you're kind of looking at, the distribution of what tests are done out there. the Malick 3, the Bray P1, and the Olson bicarbonate test are the most common three that are done in the United States. And you can kind of see the distribution here in terms of which are the most popular. But those three make up most of what we're dealing with. So therefore, those are the three that I've provided information for you in the ABCs and of how to interpret a soil test document on Learning Suite. So we do look at those three, but I just want to kind of show you this, and similar for potassium. Now, if you want to kind of say, well, aren't the values the same? I mean, if you're extracting phosphorus, shouldn't you be getting the same value? And that's not true. If I'm extracting nitrate, getting back to that, or sulfate or chloride, it shouldn't matter what the extractant is. I should get the same number because I'm trying to extract the total amount. But on these indexes, they're not built that way. They're going to extract different amounts. So for example, let's say I was just going to extract with water. That would sort of be the least aggressive. I would get a really low phosphorus number if I was extracting with water. Now, if I was extracting with hot concentrated acid, I would extract a lot of phosphorus because more of those precipitates are going to dissolve. So where is the right number in there? These different extractants kind of have different values. Now that seems complicated, but if you think about it, it's really not. Think about temperature. If you told me it's 31 degrees, I would say, I don't know what to do with that number because you haven't told me everything I need to know. I need to know what scale you're using. Now, if that's in the United States, it's probably Fahrenheit, and that's just below freezing. But if that's France, it's probably Celsius, and 31 is pretty warm. So it's important to know which temperature scale I'm talking about. Similarly, I need to know which phosphorus extractant I'm using in order to interpret it. So that's what we're looking at here. And you can see, again, this is an IPNI document. And for example, here's this category right here. You can see this Malick 3 ICP value of 66 to 90. What would be equivalent for an Olson P sodium bicarbonate test is down here. It'd be about 39 to 57, about half. In other words, the Olson bicarbonate test is going to run about half of what a Malick 3 ICP test is going to do. And is that a problem? No, unless I'm not using the right scale. If I'm trying to interpret Fahrenheit values using a Celsius scale, it ain't going to work. Similarly, I can't interpret a Malick 3 value of phosphorus on an Olson test and vice versa. I need to interpret it with the right numbers. And so this is just an example of that. Now, again, in my document, I've kind of simplified all of this in this ABCs of how to interpret a soil test document. And I've given you some numbers of what you need to know in terms of how to interpret this. So I just want to give a little background, though, why and how we get these different tests. So we gave the example of phosphorus here, but the same is true for these other nutrients. The method is usually less critical for like potassium than it is for phosphorus, but the principle is the same. Okay, let's kind of talk about fertilizers for a minute. We get different kinds of fertilizers. By law, fertilizer products have to show the guaranteed analysis in this order: nitrogen first, followed by P2O5, as phosphorus is P2O5, and then potassium is K2O. So for example, a 16-8-16 is 16% nitrogen, 8% P2O5, 16% K2O, and that's probably a blend. And in this next one is 4600, that's urea, 46% nitrogen, no phosphorus, no potassium. Here's the most common, by the way, urea is the most common nitrogen fertilizer that's sold in the world. The most common phosphorus fertilizer are these ammoniated phosphates. Monoammonium phosphate here is 1152, 11% nitrogen and 52% P2O5. Now that's actually all in the same granule. It's not a blend. Every granule of MAP has the same amount of nitrogen and phosphorus. And I'm going to explain that here in a minute and why that's important. Potassium chloride is the most common potassium source that's sold in the world. 60% K2O. In some cases, the companies are going to show the other nutrients. Probably the most common one would be ammonium sulfate, which has 21 and then 24, which is 21% nitrogen, 24% sulfur. And it kind of, even though they're not required to do that, they typically will want to do that, so you'll know what else you're getting in your fertilizer. This is also important. Now, this is really unfortunate. When the fertilizer laws were being made, they thought that the phosphorus was P2O5 and that K was K2O. That's not true. When we buy fertilizer, these things don't actually exist. You can make them in the lab, but they're not in fertilizer. They actually exist as phosphate and as potassium K+. That's how they actually exist. But we're stuck with it. And so I wish it wasn't that way, but we're stuck with it. It's sometimes important to be able to convert from P2O5 to just P and K2O to K. And so if you did the math, you would see that there's 43.7% P in P2O5. And and the rest is oxygen. It's 2 phosphorus atoms and 5 oxygen atoms. So that's the math is 43.7 phosphorus. Potassium is 83% K, and the rest of that is oxygen. There's a nice little link here in case you want to look at that more and understand that math a little bit better. And we will do some of that math, including on the unit quiz for this unit. As equally or more important is being able to determine the rate. The way I do that is I take the rate of the desired nutrient times the area of my garden, let's say, and I divide that by the grade of the nutrient. So for example, let's say my garden is 50 by 50. I've got a 30-10-20 fertilizer analysis. I want to put on 2 pounds of nitrogen per 1,000 square feet. So how do I do the math there? Well, I take my 2 pounds of nitrogen per 1,000 square feet, and I multiply that by, I multiplied the 50 by 50, that's 2,500 square feet. So I multiply those two, and the square feet cancel out. I divide by the 1,000, and then I divide by the 30% nitrogen. And when I do that, I get the answer of 16.7. I'd probably round it up to 17 pounds of that actual fertilizer to apply to that area in order to get 2 pounds of nitrogen. That's the math. Here's another one. If I wanted 2 pounds of P2O5 per 1,000 square feet, how much MAP would need to be applied? Well, I would do the same thing. I take, 2 pounds per 1,000 square feet. I multiply it by the size of my yard or garden. And then I would divide it by MAP, which I told you previously was 52%. So I'm going to divide it by that to get that number. So let's say my garden was 1,000 square feet. So 2 pounds divided by 0.52 is roughly 4 pounds of MAP that I would need in order to get 2 pounds of P2O5. I can do that same math for an organic fertilizer that's a 3-1-2. It's got very low fertilizer phosphorus in it. And so instead of dividing by 52%, I'm going to divide by 1%, which means I'm going to need a lot of that fertilizer in order to get the same amount of P2O5, which is one of the problems with some of these types of fertilizers. What is the difference in the total amount of fertilizer required of each if the area being treated is 100,000 square feet? It would be massive. If you did the math on those things right there, it would just be, we need a little bit of MAP and a lot of that organic fertilizer, because that MAP has 52 times more P2O5 in it than that organic fertilizer. So I'm going to need 52 times as much. And when we start looking at large acreages, that's really big difference. I'm not going to talk about spreader calibration just because this is already going long, but it is important. And there's some great resources here. It's important to put that fertilizer on properly. I am going to talk a little bit about some of the problems we have with fertilizers in just a minute. When we talk about fertilizers, we talk about the 4 R's of fertilizer stewardship, which is applying the right source, at the right rate, at the right timing, and at the right placement. So here's some liquid fertilizer that's being applied in the wrong place. What is the value in applying fertilizer when the soil test is high? And this is really common in the urban environment. I frequently see phosphorus and potassium soil tests that are exorbitantly high in the urban environment. I don't see that as common in farm fields because they're not over fertilizing, but we are typically over fertilizing in the urban environment. So do I keep putting on fertilizer? The answer is no, I really shouldn't, because I'm, potentially hurting my plants, hurting the environment. I'm wasting natural resources. Shouldn't be doing that. So in a lot of cases, we can stop fertilizing with, again, phosphorus as an example, without any negative impacts, as long as that soil test remains high. And if some of these values are so high, it's like, I'm not ever going to need that in my lifetime. That's how much phosphorus has been built up in these soils. So if I don't need it, I don't need it. Stop putting it on. All right, let's shift gears and talk about what about calcium, magnesium, the micronutrients. Now, in general, for turf grass, which is kind of the main one we're dealing with in the urban environment, and this isn't necessarily true with crops like in my garden or with other landscape species in the urban environment. For turf grass, we rarely need these. Now, in my garden, I'm more likely to need them. For trees and shrubs, I probably don't need them. I might need them in my, with annual flowers or those kinds of things. It kind of depends. And again, I'm just going to rely on the soil test here. Now, I say that, and here's an example of an exception. I mean, this here field is made out of sand. It's got, it had very low organic matter. And on the right here, you can see where we applied the micronutrient. We see a nice green up on this sandy low organic matter field. And that green up came from the micronutrients. So most of the time, we don't get much of a response. So we can, though, especially in sandy low organic matter soils that have, and guess what? When we do the soil tests, it shows the micronutrients are low, and we needed them. So that's why we put them on. It's based on soil tests. Now, iron is kind of unique, especially for turf grass. We used to see a lot of iron chlorosis in grass, but that's largely been changed because breeding has sort of, removed that. We still see some iron chlorosis, especially in some trees, other plants too, but trees especially, like pin oak and maples. I mean, we get some that probably shouldn't even be planted in these alkaline environments where iron is a problem. we don't tend to see too much of an iron problem in acid or neutral soils. It usually is mainly in these alkaline soils where the iron solubility is extremely low. Iron is also unique in that the fertilizer that's usually sold doesn't work. If we're applying iron fertilizer, it really needs to be in a form that's available. The most common one is the chelate iron EDDHA. Or I can apply the iron as a foliar, which we do fairly frequently, and we can get a response there too. Now, let me just kind of mention tissue analysis, sort of crossover with soil testing. Now, this is potato, and we're probably not going to do this in most of the urban landscape situations, but I like to show this as just sort of as a reality check. What I'm looking at here is taking a tissue analysis every week during the growing season on potatoes. Now, if this is my garden, I can't afford to do that. If I'm growing a whole field of potatoes, for a community garden or something, then yeah, I can do this. Or if I'm a farmer, I can do this. But what's kind of interesting is that I want to be able to, so in the case of nitrogen here, we've got some really good data. We want to stay between these two lines. Notice one thing is that the lines are decreasing. In other words, I want to start high in the season, in the early season, but I actually want it to drop so that potato plant will go into reproductive stage and make tubers. This is a really bad problem in tomatoes, for example. A lot of homeowners don't get good tomatoes because they keep their nitrogen way too high. But tomatoes want to do the same thing. Well, so you'll kind of notice in this case that we started out okay, but then we dropped low. Then we overcompensated through some in-season applications, and we actually ended up just a little bit too high. So that's kind of important. And that's, some of these things are pretty sophisticated, like potato. The average gardener isn't going to do that kind of stuff, but the reality is if you want to be a great potato grower, that's kind of what you need to do. You'll notice here in phosphorus, we started out good and we stayed above the line. There isn't two lines on any of the rest of these. We only are showing the bottom line. So we need to stay above that point. It's not too bad for most of the rest of these if we get too high like it is for nitrogen. So we were good. Phosphorus was good. Potassium stayed above the line. That was good. Sulfur, we stayed above. Calcium, magnesium. Notice here on the zinc, though, it actually started out okay, but then it dropped and kind of was a problem. I'm going to come back to that in just a second. Copper kind of did the same thing, although it's less clear what was going on there. The boron and the iron basically stayed okay. So here's an example. Here's where the soil test isn't always perfect. And sometimes I need to kind of calibrate myself. And so, yes, I start off, I trust the soil test, but sometimes, remember those anomalies we saw? That happens. And so this is kind of one way that I can, using tissue sampling, I can say, hey, maybe my soil test needs to be tweaked a little bit. This is a good example. Soil test was on the zinc was medium high in this particular situation. And it was calling for no zinc. But when we did the tissue analysis here, this is the one I just showed you. It actually dropped below the critical level by the end of the season. So it wasn't perfect. Now here is kind of a contrast. This one, it actually said we needed zinc, and we put some on, but we more or less stayed above the critical level through the season. So tissue analysis can kind of be used hand in hand with soil testing, and that can be a little complicated, but I really like to look at both and not just rely on one or the other. So for turf grass, again, that's mostly what I'm dealing with in the urban landscape. Getting the nitrogen and sulfur right needs our greatest attention, and it's the most difficult part of this. The phosphorus, the potassium, the micronutrients are relatively easier. I can kind of just follow that soil test and maybe, make some tweaks here and there based on tissue analysis. But I've really got to get the nitrogen and sulfur right, especially for the turf grass. Now, soil testing isn't the best for these two. Why? Well, let's just look at this data. Look on the bottom. Here's phosphorus, and this is taking samples throughout a growing season. Now, the only reason we did this was to demonstrate this. You wouldn't do this, but we did because we were trying to look at it and see, well, how does this thing change during the course of the season? So the variation was about 8% for phosphorus and about 6% for potassium. And that's pretty low. That means that the soil test is, even though the plant is taking up those nutrients, the soil test is kind of maintaining. So that's good to know. But look up here with the nitrate and the sulfate, man, they got massive variation. And that's because of plant uptake and weather and fertilization. I mean, we're kind of seeing all kinds of things happening. So you can see some of these spikes here for the nitrogen. That's when some fertilizer was applied. And so we see some crazy numbers like that. And what that means is I'm really not as dependent on soil testing for those two as I am as P and K and the micros. So again, coming back to this, I'm measuring the total amount, and I do look at it. For nitrogen, nitrate is generally the form that's plant available. So that's why we test for it. We want to avoid excesses in the soil. So I do look at the soil test, and if it is really high, I'm asking myself why. In general, we want to spoon feed this throughout the growing season. So we don't want these big spikes. It'd be nice if we could just kind of steadily supply that. We often test for nitrate and sulfate, and again, I do look at those, and I do mostly if they're just really high, it makes me ask the question why, and I try to figure that out. Maybe it's because there's a bunch in the irrigation water, and need to test the irrigation water, which we'll talk about in another unit. If I just fertilize, that kind of explains it, and then I just don't pay attention to it. But if it's really high for some unknown reason, then I'm going to be kind of a detective and try to figure that out because I don't want it really high. Now, sulfur, the soil test is really poorly correlated with plant uptake. However, soil organic matter is actually a pretty decent predictor of sulfur response. If I have organic matters less than 2%, I'm got a reasonable chance of getting a sulfur response. The higher I get above that, the less likely I am. Now it's not a perfect, like, okay, below 2, I'm going to put it on, above it, I'm not. That's not how I do that. But I'm just saying that in general, the higher that organic matter, the less likely you are to need it. Some other things on that soil test would include organic matter, as well as the cation exchange capacity, which we talked about, the CEC. Organic matter is a pretty good indicator of high soil quality. It helps us with water and nutrient holding capacity. It does contain nutrients, and when microbes decompose it, they release into the soil, and so that's good to know. The CC measures that, and CC basically is looking at organic matter plus clay, the colloids, and that's telling us how much nutrient and water holding capacity we have. Now, one of the problems with that is that sometimes that'll show up on a soil test, and usually it hasn't actually been measured. Instead, it was estimated based on pH, and then the potassium, calcium, magnesium, and sodium. They'll take those numbers, the lab will, and they will estimate the CEC. Most of the time, that's fine, except for if you have a calcareous soil. So I'm going to show you an example of that where that's not accurate. You shouldn't bank on that number. In general, sands have CECs of less than 10, loams are somewhere in the teens to low 20s, and clays tend to be more than 20, 30. The more clay, the more organic matter, the higher those CECs. So it's not just about clay, but that's kind of where they tend to be. Sandy soils tend to be low in organic matter, so that kind of goes hand in hand, and clays tend to be higher in organic matter because they tend to be cooler, and so organic matter doesn't decompose as fast. That's why. Now, I get asked all the time, so okay, fine, all that's great and good, but what's your approach? How do you actually do that? Well, what I do is I get a good program for nitrogen and sulfur. I do refine it over time based on NDVI. So NDVI is normalized difference vegetative index, which is sort of a greenness indicator, a plant health indicator. We will get that from satellite imagery, drones. I even have handheld units that I use. Most people don't have that, and so honestly, you don't really need to do that. But you should be able to use tissue analysis and verdure, which is color. And so I look at that stuff, and that kind of helps me fine tune this thing over time. Now, I've listed some things in the ABCs of interpreting a soil test in terms of values for nitrogen and sulfur. So I'm not going to talk about that here. You're going to go in there and look at those values when it's time to make a recommendation. So, but that's essentially what I do for those. For the other nutrients, I base it on soil tests. The P and the K, my P and K rates are based on soil tests. I usually do soil testing every 3 to 5 years, unless I got a problem. If I got a problem I'm trying to fix, let's say my pH is really low, I might want to pull another soil test. Sometimes in really high value properties like a National Football League stadium field or a golf green, on the PGA Tour, we're going to sample those more frequently because we are watching them more carefully. But in general, for most of us, honestly, 3 to 5 years is probably good enough unless I got a problem. Let's talk about the fertilizer again. Coming back to some of the questions that we're going to deal with right now. Homogeneous pellets versus blends. So what you've got here on the left is a homogeneous fertilizer pellet or granule. And on the right is a blend. And what does that mean? Well, the one on the left, every single particle in there has the same nutrient concentrations. They're all the same. But this one on the right, this is actually a blend of different kinds of fertilizers. I've got some urea, and I've got some potash, and I've got some MAP and some other things in there. And they basically went and pulled these individual products off the shelf, and they mixed them together to make this blend. And that's not necessarily a bad thing. They certainly have their place, but there is some problems with these blends, especially for certain types of plants. And that would be mostly things like turf grass. So every individual turf grass plant has a very narrow cylinder of roots. And so, and there's others too, like onions and, some other things that just don't really spread their roots out. So if I have a fertilizer granule every, 5 inches, I've got some grass plants that are getting it and some that aren't. And that's a problem. Now, if it's corn, it doesn't matter because the corn roots are spread out so wide, they're going to get it no matter what. Maple trees or most of my shrubs and my trees and, frankly, most of the plants in the urban environment are going to be fine with one of these blends, but turf grass, not so much because of its narrow root cylinder. The other thing that we need to think about is particle size. And we talk about the size guide number, or SGN. And the bottom line is the larger the number, the larger the size of the particle. And I'll show you why that's a problem in just a minute, or right now, actually. So the one on the left has 150 size guide number. If we applied that at 200 pounds of this product per acre, this is the distribution. Compared to the one on the right with a higher size guide number, which means I got bigger particles. Now, it's the same amount of fertilizer going down per acre, but it's just not as uniform. And so, and again, if that's a corn plant that's covering that whole area, so what? But if that's turf grass, and I got turf grass that's growing down here in this bottom left quadrant, I've got no fertilizer. And so that's a bit of a problem. So I want better uniformity of distribution for some plants. Now, again, the other problem with this is we get different densities in these blends. They're going to grow, heavier particles are going to go farther. And so if I'm spreading fertilizer with a broadcast spreader, which is typical, I'm going to get, some weird patterns in terms of those blends. So that's another problem. So even with corn or other things, we could be getting some problems in that way, so I got to be careful with the spread. Finer material is going to stay closer to the center of where the spreader is. So we see this all the time. We see striping, and things when people don't do this right. Now, also this bottom comment about tire track to tire track, it's important to have complete overlap when I'm spreading fertilizer in order to kind of avoid some of this problem. I want to reduce the chance of striping. So similar to irrigation, where I want head-to-head water coverage, so I have complete duplication, I want the same thing with fertilizer. The first time I go over it, I want to make sure I come back and I'm coming back a different direction. And I'm basically, let's say I'm doing my front lawn. I'm going to walk one direction, and let's say my spread is 10 feet on each side. Well, I'm going to go walk down and spread my fertilizer, and then I'm going to turn around and I'm going to come over and I'm going to come back 10 feet away so that I've got complete duplication of coverage. Now, the reality is, like when I'm doing my lawn, I actually do 4 times because I will go one direction and then I will go the other direction. Now, I may not be able to afford to do that if I'm fertilizing a huge property like a big city park or something, but for my house, I do that so I get better uniformity. Another problem that we run into is just, fines, particle size segregation. This is a bigger deal with bigger spreaders. You put these dry products, if I got a whole bunch of fine material, it's going to just settle at the bottom and I'm going to get some poor distribution. So that's another thing to kind of think about in terms of quality of material. What you really would like, ideally your fertilizer's got the same size particles with no dust, and it's a homogeneous blend, especially for turf grass. Again, not as big of a deal for some other plants. So, we see this kind of thing. Here's a very uniform fertilizer on the left, which is highly desirable, versus this one on the right, which has got all kinds of sizes and shapes and densities, and I'm going to not get as good of a spread. So those are all important things to factor in as I'm looking at fertilizers and spreading. I might get some problems in the if I don't do this right. Let's also talk about slow controlled release fertilizers. In general, these are beneficial for the environment. I tend to get more of the nutrient into the plant and less being lost to the environment. Good news is they have become increasingly affordable. They tend to cost more money because of the technology that's in them. But, so sometimes though that, the benefit, I can put on less product and I might actually spend less total money, but again, they tend to be more effective, and sometimes I get better color and plant health by using them. We get different kinds. We get some things like IBDU, which relies on decomposition by chemical and biological processes. So the nitrogen that's in IBDU releases slowly over the course of the season as it breaks down. This big, long molecule containing nitrogen breaks down slowly. We get coated products such as polymer sulfur coated urea. That's another control release. We get some bioinhibited things such as urease or nitrification inhibitors that slow down microbial activity. So we get different types and different kinds of effectiveness and applications. And I don't really have time to cover all that right now. It's just important to do your research, make sure the product's been vetted by third-party folks like myself. Getting back to this 4 R's, the source, we want this quick versus slower controlled release. A lot of times we're using based on, price, but in general, we'd rather be slow controlled. Traditional products versus, biosolids or liquids versus certified organic. Lots of good questions. There's lots of products out there and hundreds of them. A lot of times we're looking at dollars and realizing that, convenience is also a factor. What added nutrients am I getting? I might want to look at that as part of the total package. In the case of nitrogen, I need to think about loss mechanisms and, am I going to lose that fertilizer? Those are things that I need to kind of understand the nitrogen cycle. I also need to understand the timing of release and when my plants need that fertilizer. Those are all things we might want to think about. It's important to think about the time of year. I typically want a steady supply of nutrients throughout the season, including early season when emerging from dormancy, when sometimes the soil is cool. And so sometimes we need to give us a little fertilizer right at the beginning just to give it a little kickstart. In some cases, we need late season fertilizer. Case of turf grass and other perennials, sometimes that's when the roots are being built and we're storing up things for the winter. And if I'm nutrient depleted, that doesn't happen very efficiently. So we do need to not be nutrient starved. But for other things, potato would be a contrast to turf grass. I mean, it needs it needs a little bit early, but it needs most of it kind of during the summer, steady growth when it's really growing rapidly. And then we don't want to put any fertilizer on it late. That'll just be wasted. Time of day is also important, especially with nitrogen. We get more losses if it's hot, humid, windy, and especially if I'm applying a liquid to the foliage or to, like if I've got a lot of thatch on grass or to like in a garden, I'm applying fertilizer and there's a lot of residue from plants there. Those kinds of things all result in more nitrogen loss. If we think about the nitrogen cycle, we need to remember that nitrogen ends up as nitrate, and plants can take that up as well as microbes. But everything in the nitrogen cycle kind of is moving in that direction towards nitrate. We can lose that to denitrification. We can get lateral flow to surface water. We can also get vertical flow, we call leaching, to groundwater because nitrate's so mobile. So it's kind of behooves us to use these control release fertilizers because it kind of helps slow this down and we get less loss. We actually lose about greater than 10% of the nitrogen if I'm using traditional quick release fertilizer like urea or ammonium sulfate. Now I can use that. One good practice is to make sure I put it on when it's cooler, and I immediately need to water it in with about 1/4 of an inch of water to get it down into the soil. So I'm going to lose less versus applying it on a hot, windy, humid day where I'll lose a lot. I've seen as much as 50% or even 100% loss in some studies we've done when we apply it at the wrong time of day. So some important considerations: the timing isn't always what it's claimed. I'm going to show you that data here in just a minute. It's based on temperature at the soil surface, and then what time of year. Let's, in order to talk about this, let's talk about polymer coated urea. We've done a lot of research on this. The idea is that you get this polymer that's around the urea. It prevents it from reacting with the soil. As water moves in, eventually the nitrogen moves out into the soil, but it's a slow, controlled process. Here's some data that we did. This is some of our data. And what I'm looking at here is I'm looking at ammonia volatilization. So this is gas loss that goes into the atmosphere. It's a waste. It's an environmental problem. Every one of these spikes is a day. So you're looking at about 20 days over the course of this trial. And you'll notice that we, even with the control is unfertilized along the bottom here. Even the control is getting some. I mean, we get background levels that this is a part of the natural cycle of things is to have this happen. But when we start putting on fertilizers, such as the red and the green lines here, we are actually greatly increasing the amount of nitrogen that's being lost to the atmosphere. However, when I'm applying the same quantity with a polymer coated urea, this is the in-between line here, I've greatly shut down the nitrogen loss from ammonia volatilization. So if you compare the green line with this polymer coated line, it's a tremendous benefit. So that also enables me to put on less nitrogen. So because I'm more efficient. So this is good. And by the way, this stuff was watered into the soil. This was not sitting out on top on a hot, humid day. This is just kind of normal, what's happened. If we would have made it hotter and more humid and windier and left the nitrogen on top, these spikes would have been much, much higher. But so even into good management practices like this, we see an advantage for polymer coated urea. Same is true for nitrous oxide, which is another gas of nitrogen that's lost. This is a very potent greenhouse gas. You can see that we almost completely shut down the nitrogen loss. So let's kind of talk about how long this lasts. This is actually a little bit of a problem. Now, I've worked with this duration product, really good product. However, there's some misunderstandings with regard to this. Here's the thing that we hear about. We hear about people, saying, well, this is one application. I can put it down once and it's going to last me the whole year. And we get these different products such as duration 45 or 75, 120, 180. Those numbers reference how long they are expected to last. Now that's based on some data. Here's some data that they collected, the company. When the temperature is static like in a laboratory where this test was done, those are the kind of release rates you get. You get similar things from if you buried it in the soil, but I'm going to show you some interesting data. First, though, let's talk about sulfur-coated urea, similar to polymer-coated urea. Show you some data on this too. And then we get polymer sulfur-coated urea, which is both coatings. All right, let's kind of look at this data. Let's pick this thing apart. It's a lot of things here, a little confusing, but let's just kind of look at what we got here. We're going to compare a couple of different fertilizer sources. Duration 120 is a 120-day polymer-coated urea product. Duration 75, 75-day product. We're going to compare incorporated into the soil compared to a surface application. So like you'd have with turf grass or basically almost everywhere in the urban landscape, except for maybe a garden that gets tilled in. So we surface versus incorporated. So this is incorporated up on top. This is the surface applied on the bottom. We're evaluating this over time, about 130 days or so is what you're seeing. We're comparing static, which is, lab conditions, or that would be somewhat akin to what is in the soil. If you get that fertilizer into the soil, the temperature doesn't really fluctuate much in the soil. And so that's going to be simulation of what happens in the soil compared to the field conditions, which is what would happen when it's out on top. And so these are fluctuating temperatures and these are static temperatures. So that's, again, what would be similar to what you'd have in the soil versus what you'd have sitting out on top. So notice the individual data points. These are smooth lines. I get R squared values. You get the idea of the science here. Here's the fertilizer released in a controlled linear fashion at about the right timing when it's incorporated under field conditions, which is this guy. However, the fertilizer under a static temperature regime didn't complete its release after 120 days. And more importantly, when the surface applied, the fertilizer under field conditions released much faster. It was basically done, even though this is a 120-day product, it was basically all released in about 35 days. So that's kind of the bad news. It doesn't last the whole season. The good news is, though, is we still had those benefits of we didn't lose much to volatilization or denitrification. It's still very effective, but it just doesn't last the whole season. Our data actually shows we can, if we do 2 applications instead of 1, we can actually get away with just 2 applications of this, even in the most rigid environments. So, okay. What about the quality of the coating? Sometimes not all of them work. Here's one that, supposed to be slow release. This is a polymer sulfur coated urea. The whole thing released basically in about a week. Here's a sulfur coated urea that all basically released in about a week. So, it's important. Not everything works as it's claimed. That's kind of the point there. Well, just sort of getting to the last things here on the soil test. That nitrogen and, those nutrients are important, but we also get salts, and we need to realize the nutrients are salts. And plants need salts, and you and I need salts, but too much salt can kill us. So we do watch that. We watch the salt concentrations. We also watch the sodium concentrations. If we get excessively high sodium levels in the soil, that can destroy the soil structure. And if we do, we need to apply a soluble calcium source, such as gypsum, in order to raise the calcium to sodium ratio. We don't add limestone, by the way, because that's not a soluble calcium source. It does contain calcium, but it's not soluble at the pHs where we usually have these sodium problems in the alkaline soils. So anyway, we do watch those things. I'll show you a quick example of that here now. What I'm going to do right now is look at, I'm going to go to a sample of a soil test report. So here's a sample from a good laboratory. And let's make it bigger so you can kind of see it easier. But we see lots of things. We get all kinds of, we got 3 different samples here. We're looking at a whole bunch of different parameters. Here on this line up on top shows the method. So getting back to the phosphorus thing, here's the Malick 3 method. I also asked the laboratory actually to run the other 2 most common ones. So you'll notice down here at the bottom, I actually have the Bray and the bicarb values as well. So I actually have all 3. And that's the reason I did that is for a later activity in class. But again, so this is kind of the soil test report with the different values in terms of concentrations up here at the top. In the middle, I get fertilizer recommendations if I had asked for them, which we didn't. And so they didn't give them to us, except for they did give us the lime recommendation, which comes, with that buffer pH. Now notice, like I said before, the buffer pH is only done on these guys that are acidic. This third sample here has a pH that's alkaline, and there's no need to run the buffer pH test, so they didn't. Another thing that I want to point out on the soil test are these percentages over here of the cations. here, for example, here's a sodium percentage that's 15. That's kind of high. I would actually be expecting some problems. We're not going to talk about that right now. We'll talk about that more when we actually talk about saline sodic soils and waters at a later unit. But and also that is listed, how we deal with that is listed in that ABCs of how to interpret a soil test document. Just another point here, a couple of other points. Remember what I said about the lab will estimate the CEC. This is a calcareous soil. How do I know that? Because they did this excess lime test and it was high. So therefore we had to measure the calcium carbonate, and it's 5%, which, so this is definitely a calcareous soil. And so the problem is when they estimate this, you're getting a false high reading. This soil does not have a CEC of 43. Does not. It's getting a false high because of the calcium that's in the calcium carbonate. Now, these other two, the 4 and the 24, those are actually probably pretty close to true CECs because this is not a calcareous soil. Kind of the last point here, I also had them run the aluminum levels on these acid soils. And the reason is that, you'll notice that both of these have a pH of 5. They have identical pHs, but they have different levels of aluminum. One of them has 8, which is actually below the critical level. And one of them has 95, which is above the critical level. So what that means is that middle sample has probably got some aluminum toxicity. And even though the other one has a identical pH, it does not have aluminum toxicity. So that is a test that I sometimes run when I have these really acidic soils, especially if I'm seeing healthy plants, even though it's pH of 5, so sometimes that aluminum test will help explain what I'm seeing there. The other thing you'll notice is getting back to the pH, again, both are pH 5, but they have different buffer pHs. And you'll notice that results in, I've got different lime recommendations. This sandy bottom field, that's the ID that they assigned it. It doesn't need very much lime, even though it has the same pH as this one that's labeled poor. Why? Well, it's because the sandy bottom has a low CEC. So it's not very buffered against change. There's not as much clay. Now we didn't do the texture analysis, but I did do organic matter, and this one has less organic matter. The sandy bottom has less organic matter than the poor. It has less than half as much. It's also just by its name, it's sandy, and so there's probably less clay in it as well. And the bottom line is I got very different CECs. So here's the bottom line and you'll need to know this for one of the questions in the unit quiz, is that CEC that's low means it's not very buffered against change. It'll change really easily. So it doesn't take very much limestone to raise the pH. And you can tell by the buffer pH. When we added this buffer to it, it raised the pH higher for the sandy bottom field because it's not as buffered against change. Compared to the poor soil, it only raised it to 6.6. So that tells us it's going to take more limestone. And the lab has some calculations that they do in order to give us that number. But that explains that why we're seeing that difference in lime amount, is one is more highly buffered against change than the other one. Just last thing is that if you go to Learning Suite and you look at this ABCs of fundamental soil test interpretations for the urban landscapes document, that's under Unit 4 soil analysis. And if we download that guy, this kind of walks you through how to interpret a soil test. I'm not going to do that here because this lecture has been way too long already, but you can kind of read through this. I've written it up. It should be fairly straightforward how to interpret that soil test. It should explain, how much fertilizer you would need, how, we do everything here from evaluating the pH to, going down here, salts, sodium, how we do nitrogen, phosphorus, etc. And so this is a helpful guide. It kind of skips over some of the sophistication of soil testing and tries to kind of just focus on the basics. So even though I've kind of dived a little deeper than maybe what you need to know for your everyday world, this document is really kind of just nuts and bolts of how much you need. And so, so for example, here's target values for the 3 most common soil tests right here. Kind of gives you sort of, we would like them to be in this range. And then later on, it tells you how much fertilizer to apply if they're, below the ideal range. So, well, having said that, hopefully I didn't put you to sleep too bad. Thank you very much.